Cams on, everyone. Let's start off. Let's just brief up a bit what we did last time. There we talked about something called centripetal force and centripetal acceleration. Then we did this polar coordinates differentiation. Hope everyone has gone through this once. Again, like I said, all this thing, right? It's fine if you don't remember that because technically this is not there in the portion, but they do ask in advance. So, but whenever they ask in advance, you know what they do? They give you this equation and then they try to ask you. At the end of the day, we proved all this stuff. So in this, we are mostly interested in this one and this one. The other two, whenever they ask you, they will give you in a paragraph. Without that, they will never ask you this question directly. They did ask something like this in 2016 or 17. We will do that question also. So anyway, so this is the main thing that we derived. There are 4 terms in this. So whenever you have a system which is going in some curved path, right, you will have 4 acceleration terms. So when you go and keep an observer on this, you have to apply a pseudo force. So what is pseudo force? Mass into negative of acceleration of the particle, which is minus of all these terms. Is that making sense? In that, the one particular term is this thing. That is your centrifugal force. So then, again, this thing derivation, we don't need it. It's just a vector form. So in a uniform circular motion, luckily these 3 terms are gone. So what we have left is only the centrifugal force. So then I was giving you these examples. So let me give you these examples again. So listen to this thing. Others, keep your cams on. So we have a coin here at a distance r, and we have 3 observers. A is in the center, B is on the other corner, and C is perpendicular to this. The radius of the disk is capital R, and the coin is at a distance of small r. Clear with this? Now, if you ask person A, boss, what are the forces you're seeing on the coin, right? And let's say this whole setup is rotating with omega. So if you ask person A to draw the FBD, this is what he will say. So A will say, okay, there is a coin here. Because it's going in a circle, because I'm rotating, I'm in a rotating frame, there'll be a centrifugal force, m omega square r. This is the centrifugal force. And this is also the pseudo force. Remember, centrifugal force is not pseudo force. Centrifugal force is a part of a pseudo force. Because if you remember what is pseudo force, all these 4 terms together will give you a pseudo force. Like these 4 terms. In that, centrifugal force is only a component. But luckily in this guy, the other 3 components become 0. So this is what he will write. And he will say, okay, so the centrifugal force is pulling out. There should be a friction inside. And they will say F is equal to m omega square r. Because he thinks the coin is at rest. Clear with this? This is what A will say. Now, if you ask B to solve this problem, so if you draw the FBD of the coin, this is what you will notice. And remember, most of the times, whatever problems we have, even at a mains level and even up to a part in advanced level, this is what we will use. We will not get into all that Coriolis force and all that thing. That is just for an explanation because it is important. If I simply say this is the centrifugal force, then they can ask you some theoretical questions where you will get stuck. We will see a few models also. This is a normal reaction. This is mg. So if you ask this person, what is the acceleration of the coin? He will say acceleration is 0. A thinks coin is not moving. So from here we write F is equal to m omega square r. And F must be less than equal to mu n. So m omega square r is less than mu mg. So omega will be root over mu g by r. So as long as the disk rotates with omega less than this, the coin does not slip. This is your standard mains level question. And whenever we solve this, we keep the observer in the center, solve, your life is easy, done. Is this clear what we did? Now to get a better view, what is pseudo force and what is centrifugal force? Any doubts on this page? Aditi, Ishman, Shreyan, Pratyasha, clear with this? No. Let's ask B to solve. Where is B standing? B is standing in this corner. This is the coin here. This is small r and this is capital R. Now, if you ask B, boss, you draw the free body diagram. Now, B will say, okay, we have a coin here. The distance between me and the coin is m omega square r plus r. This is my centrifugal force because I'm in a rotating frame, right? Plus, if you see, I myself have some acceleration, which is omega square capital R. This is the centripetal acceleration of the observer. So this acceleration will give you one more pseudo force. Basically, this is your linear pseudo force term, which is this term, d square r dt square. That is a acceleration along the line joining them. So this is your linear pseudo force, which is that m into d square r dt square ka term, which would be m into omega square capital R. You're getting it? Mass of the body into acceleration of the observer in the opposite direction. What are the other forces? Friction, normal reaction, mg. Now, if someone asks you this question, what is the pseudo force acting on the body? The total pseudo force acting on the body will be m omega square r plus r minus m omega square r, which turns out to be m omega square small r. Can you see? You will end up with the same pseudo force, m omega square r. So it doesn't matter where you stand, the total pseudo force will remain same. And now if you write the equation, you will get F is equal to m omega square r, which must be less than equal to mu n. M omega square r is less than mu mg. We get omega is less than equal to root over mu g by r. You got the same answer. This is the condition for coin not to slip. Now, in all this thing, we will never do problems like this in generally, but what I want you to understand from this is, they'll ask you theoretical questions like this. They will say an observer standing at A, observer standing at C, observer standing at B. Question would be like this. What is the centrifugal force as seen by ABC? What is the pseudo force as seen by ABC? Are you getting the questions? So if they ask you centrifugal force, in case A, the centrifugal force and pseudo force are same. In case B, the centrifugal force and the pseudo force is different. But in all the three cases, pseudo force will be same. Clear with this? That's it. That is the whole point of explaining you all the differentiations. If you understood this one point, I think you are done. Clear with this? What we did? Let's take one more example. The C is also standing. Na? Let's do it in frame, is frame also. So if you ask C to do the problem, again, we are doing the same problem in all the three frames. So this is the top view, or I'll just put it the side view only. C is standing here. The coin is here. So if you ask him, remember this guy has his own acceleration toward the center. A centripetal, which is omega square r inside. So if you ask him to draw the FBD, this is how the pseudo force will be. This is capital R, this is small r. So just let me show you the top view. So he will say the centrifugal force is this one, m omega square. If I call this distance x, m omega square x. If you resolve this into two components, this will be m omega square r and this will be m omega square capital R. So those are the two components of the centrifugal force. And this person will also say, because I am going in a circle, I have a linear acceleration. So I have to apply pseudo force, which is mass of the coin, and my acceleration in the opposite direction. So you'll put one more. This is the linear pseudo force, m omega square r. And you'll observe the same thing again happening. This and this will cancel. The total centrifugal force is m omega square small r. समझ में आ रहा है? You, no matter in which frame you stand, eventually the total force will turn out to be m omega square small r. Is this making sense? This C is a very good one. If they ask you what is the centrifugal force, the centrifugal force is m omega square x, where x is this distance, root over r square plus small r square. But if they ask you the pseudo force, it is m omega square small r. I don't care where you stand, it will come out to the same. And then we do the question, same story. So we have force here. This would be the resultant m omega square r. So we get the same story again. F is m omega square r less than equal to mu mg. Omega will be less than equal to mu g by r. Is this clear, everyone? Others, do keep your cams on. Any doubts on this? Clear, Arya?
Yes, sir.
Samyak, Vanshika, Ovia? Clear with this? Confused? So basically, like I said, now what is m omega square r is the vector from the observer to the particle, isn't it? So this guy, so this is the r bar na, here when you're saying, so that is m omega square x. So centrifugal force is simply what? It is between you and the particle, isn't it? M omega square r, so r is that. Because see, when you see this whole disk, isn't this line, whole line rotating with omega?
Yes, I understand.
That way. Plus on top of it, since you have your own acceleration, uska bhi ek pseudo force lagega. So the concept na centrifugal force is part of a pseudo force. It is not the complete pseudo force. That is the main essence there. Trishi, Devanshi, clear with this? Don't worry, we'll do more problems on this. But so for now, we will always stick to observer A. Getting it? When we do problems, we'll stick to observer A. When the other terms come, I will show you problems. We will see more. But for now, just get this point. What is the pseudo force and what is the centrifugal force? Both are not one and the same. Clear with this? This is one. Now, another variation of this. So when you say centripetal acceleration AC is equal to V square by R, what is this V exactly? This V is your relative velocity with respect to the center. For example, let's say you have a wedge like this, which is going with speed V1. And let's say inside the wedge, you have a block here of mass M, which is, let's say, going with V2. Here, V1, V2 are velocities in the ground frame. Now, if they ask you to find the centripetal acceleration in this case, so it is with respect to the center. So we have to keep an observer on the moving center. Actually, we get it from there only, but I'm just putting it. So you have to go and stand on the center. What will this observer think? The block is going with what speed? He thinks the block is going with v1 plus v2. So he will say the centripetal acceleration is v1 plus v2 whole square by r, where r is the radius of the circle. So be careful with that. So that v is not the velocity in the ground frame, that v is the velocity with respect to the center. So if you actually try to draw the FBD, we get normal reaction. We have mg. Since you are going in a circle, we have centripetal acceleration, or you can use centrifugal force. Both are fine. Then we write this is n minus mg is equal to mass into acceleration. So the normal reaction will be mg plus m into v1 plus v2 whole square by r. So keep this one thing in mind. So in total, if I have to clarify everything, what I want you to remember is this. So all this mathematical derivation, right? It's fine if you didn't get much, but you have a rough idea. What we're trying to show you is when a body is going, there are 4 different accelerations. Each one will create its own pseudo force. And that centrifugal force is only part of it. I think this example should make things more clear. So make sure to go through this example once more after the class. You got it? Great. You got confused. Thursday, please ask me. Get it cleared. The centrifugal force depends on the distance between the observer and the particle. You can clearly see here. B will say centrifugal force is m omega square r plus r. A will say m omega square small r. C will say m omega square x. But if you ask them what is the total pseudo force, all will say it is same, m omega square small r. That is the first thing I want you to know. Second thing, this one, v square by r, that v is not the velocity in the ground frame, it is the velocity with respect to the center. Third thing, people get confused, sir, when to use centrifugal force, when to use centripetal acceleration. We will talk about that. So the thing is, whenever you get confused, should I use centrifugal force, should I use centripetal acceleration? You have the answer. You have to ask yourself, do I want to do this in the ground frame? Do I want to do this in a rotating frame? You're getting it? If you say I want to do in the ground frame, then use centripetal acceleration. Don't talk about centrifugal force. If you say no, I want to do in the rotating frame, then don't talk about centripetal acceleration. Then do it in the centrifugal force. Clear with this? So let's see a few questions. I'll show you with both the methods. I think that should make things more clear. There is too much math here. Let's start off with some easy questions and we'll slowly bump it up. Remember, whenever the thing is rotating, our observer will be always in the center. We will keep our life simple. We will not take all those weird observers that B and C standing anywhere they want. We'll keep him in the center to keep our life easy. It's called a death rotor. No one actually dies, so don't worry. So this setup looks like this. We have a cylinder which is rotating with omega. This is actually an amusement ride in some. It's a ride in some amusement park. So we got a cylinder of radius r. So we take a person here and so they make you stand here near the walls. Okay, man of mass m and the friction is mu. So once you start rotating, you actually get stuck to the what you call the cylindrical walls, and if you rotate fast enough, you don't slide down. So let's say this part is open. So the question is this: a person stands with his back touching the cylinder, touching the rotating rough cylinder. So the cylinder has a friction mu of radius r. So if you rotate very slowly, the man will slide down and fall down. But there is a minimum omega. Find omega so that he does not slip down. Are you guys able to visualize the picture? Let me show you something. It's an easy one, standard question, but getting the idea is important. Look at this.
Okay, everyone, just keep your heels back and head flat against the wall. Maintain an upright position at all
So
times.
there, this is your rotating cylinder. We kept some kids inside. Don't worry, all will be safe. And now we're going to rotate it.
Scared or sick, just allowed to stop, and I'll stop.
Hang on. Legs back.
There, the whole cylinder is rotating now. So basically, you can see there is a floor. Everyone is standing on it. So
Legs apart. Oh, Isaiah. Isaiah. Isaiah.
it's rotating fast. Now see, they removed the floor. Did you see what happened? There. See. Look at this thing. Look at that kid on the right side. Do you remember friction? We wrote a statement. The frictional force is independent of surface area. That means whether the kid is touching, with his full back or with only a little part of it, it doesn't matter. The friction force will be same. That's the reason he still doesn't fall down. Anyway, it looks a little scary, but yeah.
Isaiah.
Others are having fun. This guy's kid is crying.
Isaiah, you okay?
He's not okay.
Stop. Isaiah, you okay? Stop.
Stop, everyone. Get
So now they're slowing down. Now what happens if you start decreasing omega?
Land on your feet, everybody.
He'll start sliding down.
Isaiah. Isaiah.
Stay flat against the wall until the bride comes to a stop.
So there, that's our death rotor. Yeah.
So what if the kid stands on his legs on on the wall?
Bolo.
So what if the kid stands with his legs like this on the wall?
The problem वो बाद में दूसरा आ जाएगा ना रे. Now we have a torque and all other things ना. Did you ever see some people, right, when they catch the rod like this and they stand like this?
Yeah.
The problem is not the strength. You can balance yourself. The problem is your hip and torso na. This will start bending like this na. You'll start getting torques.
So that will make
Logically to socho na, when you're doing a pull up and when you're doing like this, technically your hands are balancing the same amount of weight.
Yes.
Problem is not the weight there, it is the torque. You start rotating.
Okay.
Your torso won't be able to sustain that kind of rotations.
इसलिए वो
It's like, so देखो ना, इसीलिए people take 50 kg dumbbell and they push it up and down. You try to take 20 kg dumbbell and try to raise your hands like this. You'll have a problem. But is the scenario clear, everyone? What is happening now? See, for you to understand the problem, you have to scare a kid. So this is your death rotor. A standard equation, but yeah, you got the idea what is happening. So let's see how to do this. Now, like I said, I'll do it in both the frames. First, I'll do in the ground frame. Now see, should I do in the ground frame? Should I do in the rotating frame? Your choice. So before starting any time, a rotational question, ask yourself, in which frame do I want to do? So my observer is on the ground. So he is at rest. So he doesn't know what is centrifugal force and all that nonsense he doesn't know. So now if you draw the FBD, what are the forces? Friction acting upward, mg acting downward, normal reaction. That's it. If you ask him, he will say there are only three forces. Then he will say, since you're going in a circle, there must be a centripetal acceleration, which is omega square r. So then he will write the equation n is equal to mass into centripetal acceleration, which is m omega square r. Since friction is balancing weight, F is equal to mg. But we know F must be always less than equal to maximum mu into n. So mg is less than equal to mu m omega square r. we get omega must be greater than equal to root over g by mu r. So this is the minimum speed. Anything more than this, you are safe. Anything less than this, the kid will slip. Second case, suppose if you want to do in the rotating frame. Where is my observer? The observer, like I said, we'll always keep him in the center. If you ask this person to draw the FBD, he will say, there is a friction, there is an mg, there is a normal reaction. And since you are going in a circle, there will be a centrifugal force, which is m omega square r. Like I said, when you're standing in the center, centrifugal force, pseudo force, everything is same. So don't get confused. Keep it simple for now. Generally, they don't go beyond this. So all the theory that I said is only for theoretical questions. When we do problems, we will keep him in the center. Centrifugal force, pseudo force, everything is same. Life is simple. Keep it that way. Don't confuse yourself. Getting it? But that is important for theoretical parts. Now, if you ask him to solve the problem, he will say acceleration is 0. He will say he is at rest. You're always standing in front of me. I don't see you moving anywhere, so you're at rest. Now he will say n minus m omega square r is equal to 0. End of the day, you get the same equations. F is equal to mg, which is less than equal to mu n, and you get omega is greater than root over g by mu r. Is this clear, everyone? So you take a call. You want to use centripetal force, centripetal acceleration, or you want to use centrifugal force. Just make sure you can't use both at the same time. Clear with this? So don't get confused. You can use whatever you want. You have to decide which frame you want to do it in. Clear? Let's see one more question. This is a top view. The whole setup is rotating with omega. You kept a rod. This is a rod of mass m, length r by 2. So this is x is equal to 0. This is x is equal to L by 2. And this is x is equal to L. Coefficient of friction is mu. It's a rough rotating disk. A rod is placed radially on a rough rotating disk. Did you ever do this in school? You take the duster and put it on top of the fan covering and then switch on the fan. It rotates and the duster goes and hits someone. Never did that. We used to do that a lot. He did the teacher once, and after that, he stopped doing it. So,
Sir, I've done
so
it
rod
at
is.
home with the socks.
ठीक है, you're not evil enough. So the question is find omega maximum so that the rod does not slip. If you remember, I gave an example with a coin. We are doing with a rod now. So what is the maximum speed you can rotate this disc so that the rod does not slip outside? Are you able to visualize the picture, everyone? So the side view will look something like this. We have a disc which is rotating with omega, and we have a rod like this. If you rotate very fast, the rod can just slide outside and fall out. We don't want that to happen. We don't want the rod to slide. So what is the maximum omega you can rotate so that the rod does not slide? The coefficient of friction is mu. Anyone not clear with the picture, please ask me. 0.3. Okay, let's see. That looks right, Samyak. Let's see others. I know what you guys did. Most of you took average and finished it off, na? No. You have to integrate here. Because every segment will have a different centrifugal force. Try. I'll give you a minute more. Let's see. Again, let's see the top view. So when you take this rod here, what is centrifugal force? M omega square R. But what is the problem here? Every point is at different distances. So at a distance x, if you take a small slice dx, this will have a centrifugal force, which is dm omega square x. What is dm? Total mass by total length into dx. Here length is given as r by 2. So 2m by r dx. So the centrifugal force on the rod. So every segment is being pulled outside again. So our observer is standing in the center. I'm doing in the rotating frame. The moment I use the word centrifugal force, observer is there in the center. The total centrifugal force will be integral dm omega square x. I have to add all these centrifugal forces. All these people are pulling you out. From where to where? Limits are going from r by 2 to r. Because the rod starts at r by 2 and goes till r. So dm will be 2m omega square by r x dx. This would be 2m omega square by r. That will be x square by 2. So we'll get r square minus r square by 4 by 2. I skipped a step there. 2 will cancel. You end up with 3m omega square r by 4. This is your total centrifugal force. Now, if you look at the rod perspective, rod will think there is a normal reaction. There is an mg. So there is one friction who's trying to balance you all. And this is your centrifugal force, which is 3m omega square r by 4. So F must be equal to 3m omega square r by 4. And we know friction must be always less than equal to mu mg. So from here we get omega must be less than equal to mu 4 mu g by 3r ka root. So as long as the speed is anything less than this, you are safe. Therefore, omega max will be root 4 mu g by 3r. So that's your answer. Is this clear, everyone, what we did? What is centrifugal force? M omega square r. But what is r of the rod? The rod is not a single point. There are multiple points on the rod. So every segment on the rod will have a different centrifugal force. We have to add them up. Is this thing making clear, everyone? dm part, what is dm, right? So Siddesh, dm is the mass of small segment. For length L, mass is m. For dx, what will be the mass? Unitary method, na? Total mass by total length into the small length will give you the mass of that small part. Sure? Any other doubt on this? Please ask me. All clear with this?
Sir, can you tell me how did you get the 2 in the second step of the integration?
Are x square by 2 na record?
No, sir. From the first step to second step, 2m omega square by r.
Length is r by 2 na god.
Okay, right.
The length of the rod is r by 2. Okay, I wrote L kya yahan pe. R and r by 2. Length is r by 2 na. Total length of the rod is not L. Any other doubts? This is important. Like this is how you get problems, integration plus if you see NLM, friction, everything is there. All clear with this? Let's see one more. This is important. This will come in at least 6 more chapters. Standard result, you should definitely know this. So we have a ring which is rotating with omega. Ring of mass m. And radius r rotates with omega. Now, if you look at this in the top view, when the ring is rotating with omega, you will observe at every segment there is a small centrifugal force in dm omega square r, dm omega square r. That means this ring is being pulled apart in all directions. The centrifugal force will try to stretch the ring. Again, the moment I use the word centrifugal force, my observer is standing in the center. So this ring will actually try to expand, but again, our rings are ideal, so they don't stretch. Now you tell me, if someone catches and pulls it radially, do you think it will be normal? There'll be some tension, right? Generating tension. So the whole ring will be under tension. That means there's a possibility if you rotate really fast, there's a chance the ring will crack. This is one of the problem, you will face in this high powered, engines and cars. If you take an F1 car, you can't use the same materials you're using for a regular car. Because if you have a very high RPM, the tension in that axle and the tension in that, spokes, the wheels and everything will be so high, they will literally tear apart. You have to use, low density, high strength alloys and everything. So the question is, if this is rotating with omega, find the tension in the ring. What did you, okay, found tension. No, you messed up somewhere. See, in your tension, if you put x is equal to L by 2 or if you put x is equal to L, you should get 0. Open ends will always have 0 tension. Let's get this. So how do we do this? Let me help you with this. This is a different model. Like I said, you should know how to do this thing. And remember the process. Huh? It's okay if you forget, but every time keep coming back to this. This will come at least 6 more times. We did something like this before in one of the question, but it's friction may. So take a small segment here, d theta. Now this piece is so small, the length will be r d theta here. Again, here I'm exaggerating the figure. This is actually very small piece. So what are the forces acting on this? So this angle will be d theta by 2 and this angle will be d theta by 2 because you're dividing into bisector. This will be tension. Remember this, that is d theta by 2. So this will be d theta by 2. This angle will be again d theta by 2. Because this angle will be 90 minus d theta by 2. So this will be the tension. This will be the tension. This angle will be d theta by 2. Just geometry. The centrifugal force will be pulling you out, which is dm omega square r. So if you resolve these forces into components, this component will be t sine d theta by 2. This component will be t sine d theta by 2. The horizontal components cancel out. So the tension vertical components are balancing the centrifugal force. So this story which I wrote here now, this is important. Every chapter this will keep coming. The only thing that will change is this centrifugal force will become some other force in some other chapter. But the rest of the story is the same. So do check out the geometry. Any angle that you're not clear, please ask. So just we're using little geometry. 2 sine d theta by 2 will be dm omega square r. Now, few approximations. Last time I taught you this. Sine theta is approximately theta for very small thetas. D theta is very small angle, so sine d theta by 2 becomes d theta. And what is dm again? Dm will be total mass. Always, remember what is dm? Dm is total mass by total length, which is 2 pi r circumference into length of that small piece r d theta. So dm will be m d theta by 2 pi. Anything that you're not clear, do ask. Then once you got this, you're done. Substitute everything here. 2t for small angles, this will become d theta by 2. Your dm is m into d theta by 2 pi. This is omega square r. Now, how do you know you have to do like this? You won't be able to figure out in the first time. Now we have seen this process, so remember this. 2 will cancel, d theta will cancel. We get tension is equal to m omega square r by 2 pi. That would be a standard result at a CET or a BITS direct result. But I'm more interested in the process. You take a very small piece. So the tensions, right? Both the sides is being pulled with two tensions. The two tensions vertical components are balancing the centrifugal force. Any confusion, anything that you're not convinced, how did you take the FBD? What is that angle? What is that force? What is the theta? Anything that you're not sure, please ask. So there, if you can see that the final result that we got, it is m omega square r by 2 pi. That means, let's say if you're going in a vehicle, right? And if your speed is, let's say 50, and if you double your speed to 100, the tension in that axle and the rods will become suddenly 4 times. Angular mass, it's a linear mass, right? End of the day, it is mass per unit length, right? That r got cancelled. So clear with this. So
Can you once
what
again,
happens? What?
sir, can you explain on the FBD here actually?
So we are taking this small piece.
Yeah.
There is one centrifugal force outside, and this part of the ring is pulling with one tension. This part is pulling with one tension. So there are two tensions and nothing. Yeah.
So what about the angles then?
What angle? Geometry. You can see this is a right angle triangle. This is a tangent that is 90 degrees. So yeah, that angles you can figure out, right?
Yes, sir.
Yeah, that much geometry you can figure it out now. This angle will be d theta. This is d theta by 2. This is 90 minus d theta by 2. So this is d theta by 2. A tangent will always make 90 degrees with the normal. This angle is 90 degrees. Sure with that, everyone?
Yes, sir.
Meaning for a circle it works, Arya. If you take if any other weird curve, then what will you do? So what happens if you rotate really, really fast? The whole thing will shatter. So when I was in IIT now, see, during that time, now we're talking 2006, 2007, we didn't have all these hard disks and everything. They're very expensive. A 1 GB pen drive used to cost around 2,500. 2,000 rupees almost in 2006 ka baat tha. And 2,500 in 2006 is very, very expensive. You'll get what 64 GB ka pen drive for 250 rupees now. Getting it. मतलब to imagine, IIT में I used to get pocket money 1,000 rupees per month. With the 1,000 rupees, I used to get everything done in a month. Laundry, phone bill, getting it. My, once in a every alternate day eating food outside. I think the simplest way to comparison, the samosa, the good samosa you get right now, right? That time we used to get a good samosa for around 2 rupees. I think it's around 5 rupees, I guess. 2006 the बढ़ गया था. That same samosa now, if you try to buy, I think it will cost you around 40 or 50 rupees. Now think about the worth of 2,500. I think that's the best way to compare it. It's like inflation. So India we have a theory called dosa theory. So what dosa theory says is, let's say you're earning some salary now, let's say 50,000 rupees. Okay. Now let's say if you go to a good restaurant, whatever is a good veg restaurant you can think of, and you go to a restaurant and let's say you buy a dosa, and let's say they're selling you a dosa for 100 rupees. So with 50,000 rupees of your salary and 100 rupees, how many dosas can you buy? 500 dosas. Your salary is actually 500 dosas worth. Let's say after 3 years, right? Your salary increased. Now you're making 60,000, right? Your boss asked how much you want, and after all negotiations, you made 60,000 next year or something. And in the same shop, the dosa ka cost went to 150 rupees. Now with that same 60,000, you can actually eat only 400 dosas. Even though it looks like your salary increased, in reality, your salary decreased. This is what we call as inflation. This is called the dosa theory. Okay, so during our time, so the most common way to store any data is DVDs and CDs. So every person in a hostel, we literally used to have 100 to 200 DVDs. Can you imagine? Because each DVD ka capacity is around 4.7 GB. So you used to have everything, your files, your books, your movies, your games. Games used to be horrible, right? If you have a game of, let's say, 8 GB, you need to have 2 to 3 DVDs. Now the game ka sizes are 25, 24 GB. It was hopeless. Even before DVDs, it was actually CDs. CD had only 700 MB capacity. That was even more horrible. Anyway, so I think somewhere in second year, third semester, somewhere I was coming from the class and I saw some guy selling CDs. Normally CD used to cost 15 rupees and this guy is selling for 8 rupees. I was like, yaar, dead cheap mein CDs mil rahe. So I brought 2 DVDs. Cheap mein mil rahe na, 50% cost. So I brought it and I was putting some data on it. So during that time, we used to have something called burn the DVD. I'm pretty sure you guys don't know about all this stuff. So you actually have a DVD writer inside which rotates the disc and you do all that stuff. So in that you have multiple options. You can rotate it at a slow speed or a high speed. High speed will get over in like 10 minutes my data will get printed. Low speed will take 1.5 hours. As usual, we all are in a hurry. So I kept maximum speed. Kept the DVD. I was doing my work and suddenly there is a fart karke big sound. I got scared. I switched off the computer and I was like, what the hell happened? Computer blast ho gaya and all. I opened the inside. The DVD broke into pieces. It became literally like multiple pieces. Some powder and all pieces are there. I was so scared. I opened the entire computer. I cleaned it and everything. And I was scared whether it will work or not. Luckily it worked. But the DVD got literally shattered. So the thing is, I brought a very cheap quality DVD. When it rotated such a high speeds, the tension exceeded the value and the whole thing cracked. So it would look something like this. Where is this guy?
Hello, I'm Gav. I'm Dan. And this is the slowest Slow-Mo Guys video we've ever
So they took out DVD.
Dyson. It spins really fast. We've hooked up to the mains.
So there they got a rotor there which will rotate it to pretty high speeds.
And kill the CD spin it.
So
Dan, we get
2.6.
and they kept a very high speed camera there to record it. So it's rotating.
Not yet. 2.
Fuck. Did you see how it exploded?
1,000.
So as you can see,
You can see
from
that in the
this,
slow motion. See.
2,500 frames a second isn't nearly fast enough to see what happened there. Let's look at what we got.
Right. You can see it warping. Look at that. Whoa. It's moving so much. Oh my god. Look at the shape of it. It's moving. Like the whole thing. Whoa! Oh man, that looks amazing.
That's what happens if you rotate something really
Tiny
fast.
bit. It's just like physics don't know what to do, and the CD's just like, nope, no, I'm gone, I'm out, I'm done. Again. What frame rate was that? 28,000.
They have slowed it down to 1,140 times, so 28,500 FPS.
28,000 frames a second. So that looked good. It looked. You can actually see it warping.
So they did one more in a much slower speed. You can
That's
see
the
this
thing
more
when you're
clearly. They kept some face
filming
also
this
on
many
it.
frames a second. You the actual moment where something happens.
Right there, look at this in slow motion.
Oh!
See where it's shattered?
Saw the
If you see the formula m
actual
omega
shape of the
square r by
CD
2 pi,
and the
so
cracks
bigger
in
the
it
radius, you get
perfectly
more
like-
tension. So it started cracking from the circumference. Again, why did it crack there? No matter how good material you make, there will be some impurities. So it starts cracking at the weakest spot. And from there, the crack started spreading and the whole thing just got shattered.
the direction the CD was spinning. It was like a spiral effect on the CD. Like a turbine. That was cool. Alright, so that was at 62,000 frames a second.
That's what happened with my DVD. Clear with that? Yeah, bottom will get more tension. So quite an important result. So do remember this. So this is like question and also your standard result.
So I mean,
Clear
the
with this?
tension would have exceeded the Young's
Let's
model.
see one more. This will keep coming up. You will see this multiple times. Let's say we have a rod. So this rod you fixed at one end and you're rotating the whole thing. It's like you stretch your hand and you rotate it. This is a rod of mass m and length L. And this whole setup is rotating in a big circle here. This is x is equal to 0. This is x is equal to L. Neglect any gravity. Now, when you're rotating everything, the centrifugal force will start pulling you out. That means there'll be tension in the rod. So find the tension in the rod at a distance x from the left end. I'll just give you something here. This is a free end. Free end meaning there's nothing connected here. So if nothing is connected there, you cannot have any tension there. So because how do you find tension? We cut it there. So what is there on the right side? Nothing. So there'll be no force. So you can keep that in mind. So the free ends have zero tension. नहीं tension at the वो होता है ना रे मतलब you have a mg also, you have m omega square also. But really it won't matter much here. Suppose if you are taking a pendulum and you are rotating it, at the bottom you have mg downward, centrifugal force also downward, na? At the topmost, mg and centrifugal force are opposite. So at the bottom, both add up. Is this question clear, everyone? So what is the picture? You can just stretch your right hand, and if you rotate in a circle, that is how the picture is. You have a rod which is rotating in a horizontal circle. The left end is hinged. The right end is free, so there is nothing attached. So that will have zero tension. Neglect any gravity. The rod is going in a circle with omega. Find the tension in the rod at a distance x. Arya, देखो ना, अभी we said ना, if I put x is equal to L, I should get 0, right? You're messing up your limits. whatever we are doing today, I'm telling you again, please make sure to solve them again. Questions, especially these integration based problems are tough. These are all a little different. If you just sit and try them again once more, you'll get a better clarity. You also got the same. So you're messing up the limits, Ovia. The free end should have zero tension. Look at this. When you put x0, you're getting zero tension. Tell me one thing here. Look at this, everyone. If all the centrifugal forces are pulling outside, shouldn't this point have maximum tension? All the centrifugal forces are outside. So everyone is pulling out. So that point should have maximum tension. Siddesh, I think you got it. Samyak, I'm not sure exactly. Let's see. Again, listen, how to do this thing. Again, the problem here is every point is at a different distance. So all will not have same centrifugal force. If it is one particle, your life would have been easy. So we take a rod here. Let's say at a distance x. Take a thin slice dx. And this dx is going in a circle. So what are the forces acting on this dx segment? So listen carefully here. So on this dx segment, the forces will be tension. This left side of the rod is pulling you inside. The right side of the rod is pulling you to the right side, T plus dt. So this is how we always take. So dt is the change in tension in the dx segment. Because for every segment, the centrifugal force will keep adding up. So the tension will keep changing. And mathematical convention, we always assume tension is increasing with x. Even though it is decreasing, the science will take care of it. So keep this one thing in mind. Mathematically, we always assume the functions are increasing. Whatever I'm teaching you these ideas now, it is not only about this problem. Tomorrow, when we do different problems, we get different things. We get pressures, electric fields, magnetic fields. So the idea is all the same. The integration, what we are doing, the way we are taking elements and all is same. We assume functions are increasing. That is, t increases with x. So that's why I have taken dt plus dt. You're seeing this kind of questions for the first time. So it'll be a little difficult, but you'll get used to it. Because once you see the same thing 5 or 7 times, then you will think this is normal. But to feel it normal, you need to go through this. So it will be something difficult, but yeah, let's get used to it. What is the other force I am having? A centrifugal force. Dm omega square x. Since you're going in a circle, there'll be a centrifugal force there. That's it. So write down the equations. So we have t plus dt plus centrifugal force dm omega square x must be equal to t. Dt cancels. We got dt is equal to minus dm omega square x. That, like I said, the science will take care of it. What is dm? dm is nothing but total mass of the rod by total length of the rod and the length of that small piece dx. So we have dt is equal to m omega square by l x dx. Now be careful here. Tension is 0 at x is equal to L. So when you take the limits for integration, this is a mistake most of you did. M omega square L integral x dx. If you say tension is 0, where is tension 0? Tension is not 0 at x is equal to 0. Tension is 0 at x is equal to L. This is t and this is x. Because we have a habit, right? 0 to t, 0 to x. That is not how you do that. Because at x is equal to 0, tension ka value we don't know. So I can't put 0 to x and 0 to t. And this is x. So we get t is equal to minus m omega square by L That would be x square minus L square by 2. We get m omega square by 2L into L square minus x square. That's your tension, everyone. It's a pretty good result. Check it out. Yeah.
So we have mathematically assumed that the tension
Wait one
increases
second.
with.
Audio is off. Bolo.
So we have mathematically assumed that the tension increases with x, right? So in the end, why are we getting a positive value? Because our assumption is
Where
wrong.
am I getting positive value?
So the value we'll get for tension is positive, right? For all x.
ठीक है, it is positive, so
Sir, but we have assumed the wrong thing, so we should get a negative value, right?
तो आया ना यहाँ पे नेगेटिव आया कहाँ से?
Okay. Means dt is a negative quantity as we move
dt
away.
is negative quantity ना? Who told
Hmm.
tension is negative?
Okay. इसलिए वो माइनस आ रहा है और फिर हमने
इसलिए माइनस
उसको
आ रहा है ना?
हाँ
Clear with this? You guys should definitely do this thing without seeing once. Take the question, take a rough paper and try to solve. Because these techniques, what you're using, right? This will keep popping up at multiple places. For example, if I have to show you later on when we do questions like this now, we will see later on electrostatics and all. See, you will keep getting elements like this. T plus dt, T, EQ. You will keep hearing these kind of words. So the ideas are same. Chapter will be different. Dekha, यहाँ पे भी minus sign. You get something similar. This is something in electrostatics. Then I think recently we did something. Magnetism. There, this was this question. There is some current going blah blah blah. Did you see? 2d d theta by 2, d theta by 2. And here, see, I wrote also, refer circular motion page 65. This is for your seniors notes. This we did recently, last month only. These things will keep popping up. The same thing we saw again in. So that's what I'm saying. You know, whatever you're finding it, array, what is this? It is looking difficult. It is fine. You know, do it 1 or 2 times. You will find it little better. Once it will become good. But as time passes, right, you will start realizing, you know, this will become a part of it. You will feel it as manageable. But if you keep getting scared and never do this will always be tough. Dekho, this is another chapter. Again, same story. 2t sine d theta by 2. You got something else here instead of centrifugal force. This is the second thing. If I show this in elasticity, because you'll keep seeing more weird ones, and this will never stop. I think I didn't do it here because I found it too easy, I guess. Maybe I didn't do it here because it was easy. And this was a chapter which is going on. I think I did it here. There you go. A ring is rotating with omega. So someone disturbed the ring and you got a wave. So the wave is going in both the directions. Again, see, same story I wrote here. Same result I got here. Then I use that result in some other question. So this is what I was saying. Physics, that is one advantage you have. Even though you find it difficult, if you can just learn it, it will keep popping up multiple times, so it gets revised. You will not find this in other subjects. Max may, no matter how good you are in matrices, it doesn't mean it is going to help you in other things. If we use centripetal force, can you tell how science will change? You want to use centripetal force here? Then the problem will be, we will say, we will not use this term. We will say it will have an acceleration omega square x. No? Then you will say net force is equal to mass into acceleration. Then you will write t plus dt minus t is equal to mass into minus ac, na, acceleration. If you are going in a circle, there should be a centripetal acceleration. Got it? The moment you use the word centripetal, matlab you're standing in the ground frame. Don't talk about centrifugal force. Clear with this? So whenever you get confused, na, centripetal or centrifugal, that is not the question. The question is where is the observer? Always start the question from that. Where is my observer? Ground frame, use centripetal acceleration. Don't talk about centrifugal. If you say rotating frame, then it is other way around. Clear with this? Take a break. Come back by 9:41. We'll continue from here. Any doubt so far? Chalo, come back in 5 minutes then. Let's see the next one. So we got a rod here. So the picture would look like this. So we got an L-shaped rod. Cams on, everyone. So this was O, this was B, and here you have a spring connected. And this is mass M. This was length L. This was length L, and this was 90 degrees. So you can see the picture there. And now you started rotating this whole setup with omega. So initially the spring is in natural length. Right? K is the spring constant. So the spring rate can move only along the rod. So that mass M, which is connected, so it can only stretch in this direction along the rod and in and outside of the rod. I think this is a better picture. You can see it's like a small bead here, which can just move up and down. So this can have motion only in this direction. So along this AB ka rod. So now if you start rotating this, so find the elongation of the spring in equilibrium. So if you start rotating this setup, the spring will start stretching and it reaches an equilibrium. There, let's get this. Blu-ray. Exam mein whom will you ask? Rod is breaking or not breaking? I hope the picture is clear, everyone. ML omega square near Samyak. मेरा आ रही है. Anyone not clear with the picture, please ask me. Again, let me ask you, how will the centrifugal force be? The centrifugal force will be along the line O to A, isn't it? Siddesh, that is right. We have one answer. Try. I'll give you another 30-40 seconds. Others should try, everyone. Advait, I can't see you, right? Your screen is completely blank. Just adjust your lighting and adjust your camera a bit. Vanshika, can you keep your cam on? राइट हो गया बट वो 2 नहीं आएगा रे मेरे आ रही है सी Look at this picture here. So how is the centrifugal force? This would be the centrifugal force, m omega square r, where r is this distance. Now, when this rod stretches, remember this length is L. Let x be the elongation in the spring. That means this length of the rod actually becomes L plus x, isn't it? This is not L anymore. This is 90 degrees. And if you look at this forces here, let this angle be some theta. So which force is responsible for, elongating this? So this component will be m omega square r cos theta. That is the one which is dragging the spring out. So the spring force kx will be equal to the centrifugal force ka component m omega square r cos theta. Are you getting this? The total centrifugal force is not used to stretch the spring, only a part of it. The other component gets balanced by this normal reaction horizontally, which I'm not showing here. Now, if you look at this triangle here, top view, this is 90, this is L, this is L plus x, and this is R. This was angle theta. So we can clearly see here cos theta is nothing but adjacent side L plus x by R. So we can replace there, we get kx is equal to m omega square L plus x. Take out x common, you end up with m omega square L by k minus m omega square. So the thing is the radius of the circle also changes because the spring is elongating. Clear with this? Any doubts on this? So when the spring stretches, that length AB becomes L plus X. The centrifugal force is the distance from the center. My observer is standing here. Like I said, all our problems, we will keep the observer at the center. Let's keep it simple. Don't worry about all that accelerations and everything. Don't get confused. We will see few problems on that in the end of the chapter because those things are technically out of the portion, but they do ask by giving a paragraphs. So first, let's get comfortable with the standard models and then we can see non-standard stuff later on. Clear with this? Next one. Next one. Let's say you have block of mass m, block of mass 2m, connected like this. So this whole setup is connected to a and this whole setup is rotated with omega. This distance is r, this is rough, this is also rough. And if you look at this, the picture would look something of this sort. And this whole setup is rotating with omega like this. So find maximum omega so that the blocks don't slip. So if you rotate very, very fast, what will happen? The blocks will start sliding. You don't want that to happen. How do you do? Step 1, draw your FBD. It is still NLM only. There is no difference. The only thing you learn in circular motion in this question is you put an extra centrifugal force. Other than that, it is NLM, friction ka forces, centrifugal forces, and solve. Try. I'll give you a minute or two. Root mu g r. Okay. I felt that is a little less. Root 2 mu g by 3r. Okay. You can treat the blocks as point masses for that radius. We have two different answers. Mu g by r and 5 mu g by r. Okay. Root mu g. Okay, let's see FBD. Let's draw the FBD of M block to M block. Where is my observer? My observer is on the center. What are the forces? The centrifugal force, M omega square R, tension. So first ask yourself, if there is no friction, anywhere, how would the surfaces move? If there were no frictions everywhere, observe this thing. This centrifugal force will be 2 omega square R. This centrifugal force will be M omega square R. That means the tendency of the blocks to move, 2m will try to come out and m will try to go inside, isn't it? Do you guys agree? If there is no friction anywhere, the 2m block will have more centrifugal force. So that will actually try to come out and the block m will try to go inside. So the frictions will be like this. This will be the friction F1. This one will be friction F1. So if you don't put the direction of friction properly, you'll get wrong answers. This is F2. This is 2m omega square R. Please check your free body diagram. So if there was no friction, the 2m omega square R will dominate. You're done. So what is this balance here? So tension will be m omega square R plus F1. Since they're about to slip, we will be maximum forces. So this would be m omega square R. I think I'll substitute in the end, and this will be 2m omega square R. Will be tension plus F1 max plus F2 max. So take tension and substitute here. That would be m omega square R plus 2F1 plus F2. So m omega square R, what is F1? 2 mu mg. What is F2? This is 2m. Mu 3 mg. Be careful, the normal reaction on the ground is 3 mg. This normal reaction is mg. So that would be m cancels off, omega square R is equal to 5 mu g. So omega will be root over 5 g mu r. This is your maximum, everyone. Anything more than this, the blocks will slide. See where it went wrong. See, did you mess up your FBD? Did you write the forces wrong? Did you take n wrong? See where you messed up. The F2 will be mu into N2, that N2 will be 3 mg, the total weight of both the blocks. Clear with this? Trishi, clear with this? Siddesh? Clear? Sudiksha? Vanshika? Srihari? Rudransh? Any doubts on this? Aditi? Advait, clear with this? Let's see one more. So again, see, don't think like, oh, what is this? But ask yourself, what did you do exactly? You just added centrifugal force and the whole thing looks like NLM, isn't it? That is the only thing that is happening there. See that we got a disk here with a groove. So you took a disk in the middle, you made a small slot kind of thing. This is a smooth groove on a rotating disk. Again, same example. If you put a, a duster or something on top of the fan and you switch it on, this is going to get pushed out. So here you kept a slot. So when this thing starts rotating, this thing will come out. So if you look at the top view, this block is starting somewhere here. So the centrifugal force is dragging you out, and because of that, you will gain speed. So find the speed when it comes out of the groove. With what speed will this come out flying? That is the question. I can't be. So then you will get 2T na Siddesh. What is T then? Do you know the value of T? If you consider both as one block, there is a tension here, 2T. If you know the value of tension, you can do that. Do you know the value of tension? No, you don't know. That's why you have to draw two separate FPDs. And think about this. When both the blocks try to move, will both the blocks try to come out? One is coming out, one is going in because of the string. They don't have acceleration in the same direction. Let's get this, everyone. Anyone confused with the picture, please ask me. So you have a disk with a slot. You kept the block at a distance of r by 2. Once you start rotating, the disk will start getting pushed out. Who is pushing out? Centrifugal force. Meaning if you stand on the rotating frame. That's more easy to see. The question is with what speed will this come out of that slot? Omega r by root 2, root 3 r by root 2. Let's see this thing. It's a small trap though. So this is a slot. Let's say after some time, the block has traveled some distance. Let this be x. So what are the forces acting on this? If you observe, there's only one force acting on this, m omega square x. And acceleration. So the centrifugal force is dragging you out. So m omega square x is equal to m into a. So we get a is equal to omega square x. So this a is nothing but dv by dt. V dv by dx because you want in terms of x. So we get v dv is equal to omega square x dx. 0 to v. Remember the limits will go from r by 2 to r. So v square by 2 is equal to omega square by 2. This will be x square. Limits will go from r to r by 2. 2 will cancel. This is r square minus r square by 4. This thing is 3r square omega square by 4. But there's a small problem here. This is your radial velocity. So what you got here, v root 3 by 2 r omega. This is your radial velocity. So this is the speed with which you are traveling in the groove. But if you actually look at the disk and the ground frame, what you will notice, this block, right, is not actually going in a proper thing. It is actually going in a spiral. So when it flies out, it is flying out at some weird angle. So you get two velocities. This is your v radial, which you calculated. Because think about it. How is the centrifugal force? Away from the center. So what will it give you? It will always give you velocity away from the center. Plus, you also have a v tangential. Because you're going in a circle, you'll also have a v tangential, which would be r omega. Isn't that? If you're going in a circle of radius r, what is the speed? R omega. What is your v radial? Root 3 r omega by 2. You can try this and see. If you put something on your fan cup blade and switch it on, it won't come out along the radial direction. It will actually fly at an angle. So this particle, when it comes out, it has two speeds. One a tangential speed and one a radial speed. So the speed will be, square them and both add them. Root over v radial square plus v tangential square. That would be r omega, and that will be 3 by 4 plus this, so root 7 by 2. Right, Arya. Right, Samyak. So they show, yeah, most of you got it. So the most common mistake is this. They'll integrate till here and they think this is the answer. No, this is not what I asked you. This is the speed with which you are pushed out of the hole. Great, but that velocity is radial. But when you come out, remember, don't forget, it is actually spiraling. So there's also a tangential velocity. This is actually the path of the block. Clear with this? Any doubts on this? Great. Let's see a few more theoretical questions.
Sir, how did you get that equation, sir?
Which equation?
Sir, after the second step, sir,
This
we
one.
get to dx square, sir, when we take the dx in the bottom to right hand side.
नहीं ये x था वो. ठीक है?
Okay, sir.
That is x. It's not dx. It is x only. We didn't write it properly. Let's see a few theoretical questions. Let's say you're sitting in a giant wheel. Pretty sure you must have gone in one. So we got a giant wheel which is rotating with omega. So let's say when you're sitting in a seat, when you're exactly in the horizontal position here. So you're sitting like this. This is the kind of question you get theoretically. So let's say we have 4 directions. I'll show you A, B, C, and D. So this is a question like this. A person is sitting in a rotating giant wheel as shown. In which direction does the seat exert the force on the person? There are 4 directions, A, B, C, D. A person is sitting in a rotating giant wheel. So in which direction? If you're sitting in a seat like this, in which direction is the seat exerting force on you? So is it A ka direction, B ka direction, C ka direction, D ka direction? So those will be the options in the exam A, B, C, D.
So is the giant wheel rotating with a constant velocity?
मैटर करेगा क्या? Technically shouldn't matter, but yeah, meaning if you accelerate too fast, there is a chance this guy will get out of the seat and fly off in the air. But okay, let's not kill him. So we have, okay, we have 3 answers. Others, I'll give another 20 seconds. Easy one. This will be a proper CET or maybe a bits level question. Nereshman, that is wrong. If it is right, fine. If it is wrong, I'll... Let's see. Simple thing. Just draw the FBD. So on the person who is sitting, what are the forces? The seat is pushing you from the bottom, right? The seat is also pushing you from the left side. You have your own weight mg, and you have your centrifugal force, which is pushing you out of the wheel, which is m omega square r. That means if you look at the seat, so the seat is pushing you up, and the seat is also pushing you to the right. So the resultant, so the seat is actually doing 2 things. Right now, when you're sitting on your chair, observe, isn't the seat ka bottom part pushing you up and the seat ka backrest is pushing you forward? When you're leaning on your chair, the chair ka backrest is pushing you forward. The chair ka bottom part is pushing you upward. So this is the force due to the seat. So the answer is B. Easy? Next one. Any doubts on this? Yeah, B, most of you got it. An aeroplane is going in a horizontal circle with constant speed. Force due to the engine, speed V. Force due to the engines is F. The engines are generating from thrust force, which is F. So the question is like this: which of the following is the free body diagram? So options should be something of this sort. What do you guys think?
So the frames are for which, sorry, the FBDs are for
Bas
which
itna
frame?
hi question tha. This is a question. Bas. They won't tell you all the stories in the exam. You figure out. It's a mains exam. Now figure out. If nothing is mentioned, then which frame do you take? Ground frame. Always keep that in mind. In ground frame, you'll never find centrifugal force, isn't it? Centrifugal force comes in the rotating frame. So that is the first thing. Understand, if nothing is mentioned, always take the ground frame. And they won't tell you this in the exam. You can't argue with them. Clear? So in ground frame, centrifugal force will never come. So option A and D are gone. Now let's see the actual FBD actually. If you look at this plane, which is going in a circle, what are the forces? You need one force which is pushing up to balance your weight. And you need one force in the horizontal direction to provide the required centripetal acceleration. So F sine theta provides the centripetal acceleration and F cos theta balances the weight. This is like conical pendulum, everyone. Isn't it? Conical pendulum with tension used to be like this only, na? So answer is B. So the force will be in this direction. So remember that centrifugal force should not be drawn in ground frame. They won't tell you this in the any exam. They will just do it like this. So you have to assume it is always in the ground frame. Centrifugal force is not drawn in ground frame. Because centrifugal force will come when the observer is standing in the rotating frame. Clear? Simple question, but people mess it up. People put A and come. For problem solving, we draw A, right? But you need to understand. Clear with this? There. This is how they'll ask you questions. And mains also, right? Out of 25, you might find around 15 to 16 questions of this level. Advance is a different story, though. Clear with this? If they say observer standing on the rotating frame, then the answer would be A. Then they will tell you specifically. Solve the problem, find the FBD in the rotating frame. If they don't use any words like that, you just do it in the ground frame. Not only this question, any question. Find the acceleration of the block. Ground frame. If it doesn't tell you anything ground frame, you don't assume it is going with some frame. Next thing, banking of roads. Did you ever see sometimes, the roads are not exactly, flat. They're sometimes curved at an angle. Kabhi dekha? Roads are like this actually. If you ever been on this Mumbai-Pune expressway, you'll find this a lot. The roads are not straight. They're actually bent at an angle. So why do we do this? So let's say you're a civil engineer and you're into designing and construction of roads. And again, don't think civil engineers means you'll only do constructions and everything. You will also into be traffic management. Uber and Ola actually hire you a lot. So you can write algorithms on seeing like, how to do the vehicles distribution and everything. You can work on that. So curved roads are constructed. So this is the banking, right, is especially done whenever the road is being curved. We will see why. So curved roads are constructed at an angle with the horizontal. This angle is called banking angle. And this process is called banking of roads. Okay. So let's say you don't do this and you construct the road normally. Let's take a case one. Case one, you made a rough. So you have a road which is rough. The road is horizontal, meaning it is a flat road. There is no ups and downs. Curved road, but the road is curving. For example, if your society ka, if you have a ground or something, that is actually a horizontal curved road. There is no elevation there. So if you look at the top view, this is a bad design. So let's say we have a road like this. Now let's say you take your car and you're trying to go in a circle. So when you take your car and trying to go in a circle with speed v, we have already seen this. If you are going in a circle, there should be a centripetal acceleration v square by r. And the only force which can provide here is friction. The friction between the tires and the floor will provide you the required centripetal acceleration. So F will be m into a centripetal, which is mv square by r. But we know this is less than equal to mu mg. So we get a limit on the speed. So v is less than equal to mu rg. Meaning up to this speed, the vehicle will not skid. This is what actually happens on flyovers. On a flyover, if you make a sharp turns and the vehicle comes really fast, it will skid and hit the dividers. So vehicles does not, up to this speed, vehicle does not slip. That is one of the reasons. You must have seen, when you're riding a cycle, when you're taking a turn, you slow down automatically. Because if you exceed a certain speed, your cycle, this will skid. Now, the problem with this is what? This friction mu depends on the condition of the vehicle and condition of the road. Imagine morning you're going to your office or you're going to your classes. It is sunny and bright. The road is dry. Evening when you're coming on the same road, it started raining. The road has become smooth. Your car will slip. The morning when you went at 50 kilometers per hour, you're safe. Evening 50 kilometers per hour, you slip. Let's say you buy a new vehicle. You have nice tires, good grip. Vehicle doesn't slip. After using the vehicle for 6 months, your tires become little smooth. Vehicle slips. Can you see the problem? So new vehicles don't slip, old vehicles slip. Morning it rains, it slips. If it doesn't rain, it doesn't slip. Do you really want to make a road like that, where you have no control over the road? The road is completely depending on its own thing. So mu depends on condition of the vehicle and the road. So this is a very bad design. So, and we don't like this. When you make a road, you need to have a certain control. You should be able to tell the people, boss, on this road, you can go with 40 kilometers per hour and you'll be safe. So depending on friction is a bad idea. So people came up and said, okay, this is a very bad road. So case 2. Let's say, I'll take a case. Let's say the road is smooth, but it is banked. Again, in case you're wondering what is banked, the side view, right? The cross section will look like this. Let me show you. You see these things, in this F1 race and all this car racing. Can you see these roads, how these are? That thing is banked at an angle of 31 degrees. These vehicles go so fast and the track has such a sharp turns. If you make it a flat road, this will literally go and hit that barricades. So this is what I mean by banking. You have to construct the road elevated on one side and normal on the other side. So you have to lift this road on one side. So there is a certain height. So how does this give us an advantage? How does this give you control over the speed? People whose cams are not on, right? I'll just remove you from the classroom. I won't keep asking you to switch on the cams. I'm not sure why I have to keep telling you guys. So, and it is the same people who are keeping switching off. I'm telling you, switch it on. You switch it off for 5 minutes and you switch it off. I'm not sure why. If there's an issue, you can always message me. I understand. But if you're doing that, I'll assume you're just sleeping in the class. So how does this give you an advantage? Let's start with the free body diagram. So again, side view, your block M is like this. What are the forces acting? Normal reaction, I'll do this in the ground frame, right? And you have your mg. That's it. There are only 2 forces. And it is going in a circle. Same story. If you go in a circle, there will be centripetal acceleration v square by r. Resolve the forces into components. Remember, this angle is 90 minus theta. This will be n sine 90 minus theta. This will be n cos theta. This will be n sine theta. This will be your mg. So n, there will be 2 components. Mg will be 1, and you're going in a circle. This is your centripetal acceleration. So in the vertical direction, n cos theta balances mg. It's basically a horizontal circle. And in the horizontal direction, n sine theta is providing the centripetal acceleration. So if someone asks you who is the centripetal force, it is n sine theta. The force which provides your centripetal acceleration is called centripetal force, which is mv square by r. Take that n and substitute here, you end up with mg by cos theta sine theta is equal to mv square by r. So we get a v is equal to root over rg tan theta. Did you observe something? There is no friction cut term. That means it doesn't matter whether it is raining or it is dry or whether it is a new vehicle or old vehicle, it's a cycle or it is a lorry, it doesn't matter. For this angle, you can go with this speed without slipping. Now, we know in real life, this thing also actually has a, what do you call friction. So friction becomes a support, extra support. It becomes a secondary force. So on a road, when they say speed limit is 40, even if you go at 45, you're still safe. So this angle, which we have tan theta, is v square by rg. This is your banking angle. So when they're constructing the roads, the engineers first actually look at this. How much area do I have so that I can construct a curve? And the banking speed is root over rg tan theta. Let's say you're constructing a road in some isolated area and you have a lot of area. Then they would prefer to construct a road more curved. But let's say you're constructing in urban areas and where you can't do this, it has to be sharp. Now here the radius becomes small. So if r becomes small, you can see the banking angle becomes more. You have to make it more steep. So then you will say here you'll put a speed limit of 80 kilometers per hour. Here you'll put a speed limit of 40 kilometers per hour. So if you suddenly decrease the speed limit, vehicles will go slower. So there'll be more traffic jams. So you have to play around. If you have enough area, you don't have enough area. The same thing happens even with trains also. But for trains, the banking angle is only 1 or 2 degrees. It's not too much. I don't know if you guys ever traveled, on a slow train from Thane to Dombivli. Ever went on that side? Anytime if you go, right, when you are going from Thane to Dombivli, right, on a slow train, when you cross this Kalwa, Mumbai and all these stations, if you observe, I went, few times. So the train, literally, it is such a big, huge curve. You can actually see this in a map also. When you are sitting in the last compartment, you can see the engine. Literally, it is such a big curve. So if you see the map, right, you will notice that it's a huge curve. It's a big banking angle. Clear with this? Now, again, this is the case without friction. So if you have friction, it becomes an additional bonus. So how does that look like? Let's see that. And this is important, everyone. This is also there for your HSC boards. But let me show you how it looks.
Objective: to understand the road of roads. Maximum allowed speed while taking a turn. When a car takes a turn, each curvilinear section of the turn.
There, this is what I mean by a rough horizontal road. So the road is flat, but it is curved and it has friction.
Can be approximated to be an arc of a circle with a certain radius. A centripetal force must act towards the center of the arc to enable the vehicle to move along it. This centripetal force is provided by the static friction of the surface the car is moving
that is how the frictions will be there.
Normal
reactions, NG,
the
standard
maximum
stuff.
arc. The arc
He's showing all the calculations. So
the limiting
there you get a
value
speed mu r. So if you go anything faster than this, you'll start scaling.
over mu rg.
Now see,
If the car moves with a velocity greater than the limiting value,
you can see what happens to the
the
vehicle.
center.
See how it is skidding away from the center.
Banking of roads.
Now see, the same road in the morning it is dry, now it is raining. So if you're going on that curve, you don't have a problem when you're going in a straight line. The problem is always the curve.
Cannot always rely on friction as it depends on external factors such as
This is what happens to the
rain or
vehicle.
frost, which significantly decreases the value of static friction. The
You can see that what happened. It's going when it is going straight, that was
Banking
fine.
always rely on friction as it depends on
When it's taking a
external
turn, it is
factors
gone.
such as rain or frost, which significantly decreases the value of static friction. To avoid skidding of vehicles at turns,
They elevate the
outside
road.
road is raised up, which is called
There.
banking.
And this is showing little extreme, but you can see the picture. This is how the NASCAR racing will be there.
Surface of the road at a turn makes an angle theta.
So this is all that picture which I showed you. So this is how the road is elevated. One side is higher and one side is lower.
Tan theta gives the speed which, in inclination, or that the vehicle
rated speed.
When you go with this speed, doesn't matter whether it's a truck or a lorry
does
or a
not
cycle,
depend
it works.
on the mass of the object. Summary.
Is that making sense? What do you mean by slipping? So this is your banking speed or the banking angle. So as long as you go with this speed, you're safe. This is without friction. What if you have friction? Case 3, rough banked road. So listen to this carefully. This is the theory plus this is also the question. Now here we have two cases. Imagine you're going with a vehicle with very high speed. Then what is the tendency? The vehicle will try to skid outwards. Now if you try to draw the FBD. So on your vehicle, what are the forces? You have normal reaction. You have mg. Because you're trying to skid outward, you'll have a friction downward. And you'll also have a centrifugal force, which is mv square by r. So I'm doing in the rotating frame. So now if you resolve the forces, this will be mg sine theta. This will be friction. This will be normal reaction. This is mg cos theta. This will be the centrifugal force component, mv square by r cos theta. This will be the centrifugal force component. So centrifugal force will also change your normal reaction now. So your normal reaction n becomes mg cos theta plus mv square by r sine theta. Is the FBD clear, everyone? And along the plane, the centrifugal force component mv square by r cos theta is actually balancing your mg sine theta plus friction. Slightly lengthy equations, but and then we know f ka value is always equal to mu into n. So if you substitute that, so this is one equation and this is your second equation. So we get mv square by r cos theta is mg sine theta and f is mu into n, which is mg cos theta plus mv square by r sine theta. If you bring all v square to one side, and if you shift it that side, you will get the speed v max. This is your maximum speed. This will become g into sine theta plus mu cos theta into r by cos theta minus mu sine theta ka root. This is your maximum speed. If you go anything faster than this, then your vehicle will skid outwards. Check it out. So we have to be careful here. When you take the centrifugal force, you'll have two components, one along the incline and one along the normal. And here they can ask you more. What is the condition if the vehicle never slips? So condition for no slipping, that means no matter you will never slip, that means Vmax must be tending to infinity. Even if you go to infinite speed, this should never slip. If Vmax is infinity, meaning denominator must become 0. So cos theta minus mu sine theta must be less than equal to 0. So this will come out to be cot theta is less than equal to mu, greater than equal to mu. That's another pretty good question. Why don't find the condition if the vehicle never slips? If you make cot theta greater than mu, the vehicle, no matter how fast you go, it will never slip. Clear with this? Again, just look at the FBD. I just divided the components and I equated them. This is the condition for the maximum speed. You can't go faster than this. What is the other condition? Minimum speed. So if you go very slowly, then there's a tendency, the centrifugal force will be very weak. The body has a tendency to slide downward. So now if you try to draw the FPD, same story. We have normal reaction. We have mg. If you're trying to slide down, your friction will be up. Your centrifugal force will be still away from the center. And friction will be up. Same thing if you write the components. mg sine theta, normal reaction. mg cos theta, centrifugal force का component mv square by r cos theta. Friction will be up. mv square by r sin theta will be down. Equations will look similar. We get n is equal to mg cos theta plus mv square by r sin theta. Along the incline, friction plus the centrifugal force का component will be mg sin theta. There, just put f is equal to mu n, and this would be mu into mg cos theta. Focus everyone. mg sin theta. So if you solve this, you will end up with a minimum speed. This would be rg sin theta minus mu cos theta by cos theta plus mu sin theta. This is your minimum speed. So if you go anything slower than this, even then you will skid. But generally, when they construct roads, they'll make sure V minimum is 0. Think about it. For some reason, your vehicle stops. You don't want the vehicle to skid. That means the numerator must be 0. Basically, you get your angle of repose. Play with this. So whenever they're constructing the road, they'll make sure about this. So now when you combine both of them, your final answer will look like this. So whenever you have a banked road, which is also rough, the answer lies between Rg sin theta plus mu cos theta by cos theta minus mu sin theta. This is the upper limit of the speed. Cos theta plus mu sin theta. You can make it more simpler. You can divide the whole thing by cos theta on both the sides. This will become simply root Rg. This will become tan theta plus mu. Just simplification. This will be 1 minus mu tan theta. There, this is your speed limit. Clear with the three cases? Case one, you have a rough horizontal curved road, no banking. What is the problem? You are completely dependent on friction. Case two, you have a smooth banked road. What is the advantage? Independent of the mass, independent of the friction, you are getting a certain speed. What is the advantage? On top of this, if you have friction also, now if someone writes the speed limit is 40, whereas in reality you can go 40 plus or minus 20 or 30 and you're still safe. So this gives you a range. Clear with this? This whole thing is called banking of roads, and this case 3 itself is a problem. Case 3 would be like a paragraph question directly. Clear with this? So that's a little bit of uniform circular motion. So next class when we catch up, we will see few more things on this, few more on this banking part, and then we will also see something called, non-uniform circular motion, right? What happens if the particle is not going with constant speed, but it starts accelerating? So we will do that on Thursday. So okay, with that we'll wrap up for that day. And do remember there's a test online for Thursday, so make sure to give it. So any doubts? And again, I'm telling you, we have done almost like 19 questions. Please make sure to solve each and everything again. The chapter is a little confusing. There are a lot of variables, a lot of things happening. If you don't do this again by today or tomorrow, you will forget everything. So practice them, because this will be important. As we go ahead, this will keep popping up everywhere. Okay, with that we'll wrap up for that day. I'll see you guys again on Thursday, same time.